Welcome everybody as we're coming in. I'm Dan Summers, I'm the CEO of SenseAI. I'm delighted to be here and present this topic today, moderate this topic. So as you can see on the screen, the main topic of the day is how AI is being used to drive forward superfast low-dose EM, particularly for the semicon industry. And I'm absolutely delighted to welcome our two guest speakers, and particularly from Italy as well. So we have, to start off with, Professor Nigel Browning, and he's a professor at the University of Liverpool. He's also involved in the co-founder of SenseAI itself. We've got Dr. Giuseppe Nicotra, who is senior lecturer at CNR-IMM in Catania, and he'll talk about how we actually deployed this in Catania itself. So without too much further ado, let me hand you over to Nigel. What I will say is, if you do have any good questions or thoughts or points during the presentations, do stick them in the Q&A. And for those of you who don't know Zoom by now, where have you been? But also there is a button at the bottom called Q&A, and at any time fire your questions. If they're really pertinent, I may interrupt or gently challenge put them to the presenters, but otherwise we'll have a Q&A at the end of 5 and 10 minutes. So anything that's stirred or left out, please do contribute. And without further ado, over to Nigel.
Okay, thank you very much, Dan. Hello, everyone. What I'm going to do today is just give you a brief introduction for how we use sparse sampling to get the low dose and the superfast imaging out of STEM. So to start with, I think it's worth just having a quick look at how STEM works. Effectively, the way that we run the system is we form a small beam of electrons and we scan that beam over the surface of the specimen. And at each point, you collect the scattering. When it comes to atomic resolution, of course, what we're trying to do is to get the size of the beam smaller than the interatomic spacing. And if we do that, we can build up this atomic resolution image like you see on the right here. We can also stop the probe. We can do EELs. We can do 4D STEM that we'll talk about a little bit later. And so there's a whole range of images and spectra that we can get as a function of the beam position. Now, an important part of all scanning techniques, whether this is an SEM or a STEM or whether it's used for SIMS, is effectively that the beam size that we have is the same at every magnification. So if you look at the three figures that are shown here, what you have on the left is the situation that occurs at low mag, where you have large gaps between the probe positions, which are much smaller than the gaps between them. And as you go up in magnification, the probe positions get closer and closer together until they overlap, and this is where you get the high resolution image. So we have to traditionally get the beam to be to the point where we get the Nyquist frequency. So we're sampling enough to form a high resolution image. And that's where we get to on the right-hand side. The problem with that is you have to scan a lot of points, and it takes a lot of beam dose into the sample to do that. So what you're ideally looking for is a way of getting a high resolution image out of a sampling condition like you have on the left-hand side, which is what we would have in terms of a sparse sampling. Now, just to give a quick example of how you would reconstruct an image like that, here is a simple one-dimensional problem. This is the kind of thing that most people who've done any kind of science course at university have done. You have a complex signal on the right-hand side, and this signal is made up of 4 basic elements. So here it's just a sine and cosine functions. In the terminology of dictionary learning, these 4 elements are the dictionary elements for that signal. And if we know what the elements are that make up the complex signal, then we can actually just combine them together to reproduce the complex signal that we have. If we know what the dictionary elements are, then actually we don't need very much of that complex signal to be able to reproduce it. And it turns out that you can get down to about 1 or 2% of the signal before it starts to become difficult to put together. And if you're talking about low dose imaging in microscopy, even in this case, the differences between the reconstructed signal and the real signal are very small. Now, the trick comes, and what we will do with the artificial intelligence is to say that this was a very simple problem to solve when we knew what the dictionary elements are. What we use the artificial intelligence for, and a range of algorithms, is effectively to say that we can solve both the complex signal and the dictionary elements all at once with a subsampled approach. So just to show what this looks like in real life, here are a couple of images. The one on the left-hand side is of a French castle. This is actually a color image, so you can see it works for hyperspectral images. On the right-hand side, you have an image of Barbara. In the middle here, you have the dictionary that's used to reconstruct this. And what you can see is that we actually can sample much lower amounts of the pixels in the image and completely reconstruct the image coming out the other side. Now, this will translate itself into an electron microscope. So here is a set of images that were actually obtained from a microscope installed in Harwell at the RFI. On the left-hand side, you have the subsampled image, and on the right-hand side, you have the reconstruction. Now, an important part of the dictionary learning approach to imaging, as opposed to a sort of deep learning processing effect that happens afterwards, is that if you use deep learning, you have to have training data. And therefore, every time you change anything on your image, you have to have a training set that allows you to interpret it. With the approach that we use in terms of this dictionary learning, you can see in the image, we can change focus, we can shift to different areas, we can move around the sample, and all the time we're getting a live reconstruction of our image. And what that means is that we can have much better control over the dose and the quality of the image that we're getting out. To extend this a little bit further, once we're using the dictionary, we can actually look at dictionary transfer as well. And in this case, what's shown here is in the top layer is a live image obtained off the microscope. And if you look in a zoomed up on the right-hand side, you can see that it's a little bit stigmatic, it's a little bit tilted off the axis. And instead of seeing silicon dumbbells, you can actually see two of the atoms in together, and it makes a sort of oval shape. If we take a dictionary from a simulated image and use that to reconstruct our image, we can actually get back the high resolution. So what we can do in this approach is actually begin to self-correct for some of the artifacts that come in when we acquire an image. And because we can acquire it live and run this live, it means that as the user is on the microscope, all of these modifications can happen as you're actually looking at the sample. The dictionary transfer for electron microscopy also helps us look at other signals. So in any advanced microscope, we can do things like EDS, we can do EELs, we can do backscattered electron, dark field, bright field signals. Some of those signals have a high signal to noise, some of them have a low signal to noise. So in the dictionary approach, what we can do, and this example here is from an SEM, you can take an image from the backscattered electron image, get the dictionary, and use that to reconstruct what is on the bottom here, which is an EDS map. And in this example, it's just the aluminum edge. And if you go through and do that reconstruction, what you find is you actually now, instead of getting this very low quality EDS map that you can see down here, you get an EDS map that has all of the resolution of the backscattered electron image in the map. And so that gives us a much higher precision in terms of our understanding the sensitivity that we're using to characterize materials. This doesn't just apply to inorganic materials, it also applies to organic materials. Here's an example using cryofibsem. This is using the slice and view approach, where you just keep slicing off with the fib and taking your images to create three-dimensional structures. Here, the dose that we're putting in means that we get higher resolution out of the system in general, because we don't get the blurring that comes from having our extra electron dose. So in total, there are many things that we can do to control the beam. We all know if we use electron microscopy, the beam can be very bad, also can be very good to get our contrast. By using our in-painting and our compressive sensing, we can improve these subsampled images, and that means that we get much more precise control, and even in terms of the in-situ, we can get kinetic control over the things that are happening. So in total, just let me give a shout out to all the people that were involved in the work that's gone from here, and then let me hand over to Alex, who will show a little bit more of the examples of what we're doing.
Thanks very much, Dan, and thanks, Nigel, for that introduction. So, as Dan said, my name's Alex, and I'm going to be talking here just about how we are using high-speed STEM and our technology for semiconductor analysis, and a case study that we performed with Giuseppe at CNR-IMM. So first of all, how is electron microscopy used in the semiconductor industry? So electron microscopy is a very key and vital step in the workflow. So we can use, for example, SEM to analyze the bulk composition of our samples. This could look for large-scale defects, for example. And then we're going to use STEM essentially for our chemical and atomic analysis of those defects, what's happening down at the atomic scale. And where SenseAI steps into this, and I'll show you a video. So we can take here, this is an example of a semiconductor material. Here we're simply using the full image and then applying denoising using our dictionary learning approach. And then this way we can effectively be much more sure on the signal that we've acquired and how this would look. This also showcases the speed of our reconstruction algorithm. I'm going to ask Giuseppe just to step in now and say, because he was part of this during the alignment, and just ask him how he felt during this process.
Oh yeah, thanks Alex for asking. Yeah, I was really, very impressed about the speed of the reconstruction. Now, yeah, as you can see here, yeah, there's a very nice atomic reconstruction. And so, but it's for the operator on the microscopes, it's really, really important to have a system very reactive, especially when you are tuning the parameter of the microscope, such as stigmatism, focus, and so you need a very fast feedback. And so I was impressed about the feeling I had just looking at the very noisy image that sometimes in the sub-scanned is almost invisible, how you can effectively react your tuning on the reconstructed image. This was really, really impressive for me.
Thanks, Giuseppe. I'm now going to show you another experiment which we performed, which again is this idea of dictionary transfer. And in this case, the denoising is highlighted even further, just beyond the self-reconstruction in this case. And we're actually seeing a much higher resolution image, granted beyond that of which along this viewing direction, which we require, but we can see how even with a lower dwell time, we can incorporate the dictionary transfer approach to boost the signal of our images, and then to get that much more refined features during our acquisition. Again, this helps with your alignment. This helps with all of the sort of certainty on what you're actually viewing. So am I slightly mistilted, as in the previous example? Am I slightly away from focus, away from astigmatism? The denoising approach will exaggerate those features so that you can make faster adjustments during your alignments and your acquisition, and of course during your analysis. So
obviously, Alex, this entails also less being damaged if you can stay less in the specimen. This is very important.
Absolutely. So with HADF STEM, we enjoy Z contrast imaging because we can directly interpret what it means. Heavier elements appear brighter than lighter elements. But using SenseAI's approach and using, for example, the dictionary transfer or the subsampling, which Nigel showed, we can actually start to go towards a faster alignment with lower electron dose. And then if we want, we can also do the super resolution on the fly. There's no need to use a pre-trained network like you would in other techniques. And we can effectively do all these things whilst we're on the microscope, whilst it's live, without the expenditure of using more electrons during the whole process. However, what if we want more information than just the Z contrast imaging? That's where the 4D STEM comes in. So for those unfamiliar with 4D STEM, effectively it's very, very similar to our normal 2D STEM, but now we're going to acquire effectively an image at each of our scan probe locations, and these are diffraction patterns. This allows us to have a full range of the scattering information, effectively resolving in both real space and in our diffraction space at the same time. We can then do lots of different analysis methods. These include virtual detectors. We could perform this process called center of mass, which I'll come on to. We can do differential phase contrast, and also tychography, which is a buzzword in STEM at the moment, and 4D STEM, as we can recover effectively all of the phase information about our sample. So this is really great for if you have low mass elements as well as high mass within the same acquisition. However, 4D STEM is effectively limited by the speed at which your camera, which is capturing these diffraction patterns, can operate. So a typical camera used in 4D STEM may operate at 2,000 to 10,000 frames per second. There are some cameras which can operate on the order of 100,000 frames per second, but these often come with the limitation of a low bit depth and a small field of view in the diffraction patterns which you capture. And if we have extended acquisition times, this is going to lead to beam damage, potentially stage drift. So if we're going to image on the order of atoms at the scale of atoms, then a tiny minute drift in one direction is going to effectively blur out a lot of your image or make your analysis more difficult, especially if you contain defects, that sort of thing. Now, a virtual detector, very simple. It's very analogous to our fixed radial detectors, such as in our HADAF STEM. Effectively, we just do a binary multiplication of our diffraction pattern, which you can see in the middle here, with some detector. So this here is basically going to multiply by these two. We'll add them all together and then assign that to a pixel intensity value. And this means we can perform all different types of imaging, such as annular bright field, dark field, bright field, low angle dark field, all these different analysis methods within one data set. So now we have within that one data set effectively an infinite set of images which we can form. The second analysis method is center of mass. So what we can actually extract from here is to say, well, we know that if there was no sample in the way, our diffraction pattern would be nice, uniform and flat. But when there is a sample in the way, there's some local effective electric field which is deflecting our beam away from that centered optic axis. And then we can measure that and then form the projected electric field, as we can see here, or we can perform the divergence of that field to get out our charge density. This is really nice high resolution imaging, which is quite low complexity in terms of computation, but very rich in information. And that comes from being able to have access to all of the scattering information. Finally, we can also perform tychography. In this case, it's the Wigner distribution deconvolution algorithm. Now, what this is effectively doing is saying that we know that our sample got in the way of the beam, and given that posterior, how then would our sample look in that case? And it's very similar to the charge density with slightly higher resolution, and we can extract effectively the phase of our sample, regardless of how heavy or light. So we can see in the modulus here, you see actually up here is very, very dense material on the left, very light material on the right. In this case, cadmium telluride, in this case, silicon. But we can see we can get the resolution for both within that one acquisition, revealing both the light and heavy elements. We can take this all one step further and only acquire a subset of probe locations, or in this case, a subset of our diffraction patterns. So it might look something like this. Just zooming in, we can see the diffraction pattern over a subset of those locations. And we did this with Giuseppe in Catania. And then this is one of the live acquisitions. So now we can get out our 4D STEM data at a rate which is comparable to that of HADAF STEM. However, with the ability to form multiple different images within the same acquisition, we can also then make alignment adjustments. When you typically operate on a STEM, especially at high resolution, the quality of your images at the low scattering angular range, that is on your bright field, be slightly different alignment parameters to that for dark field. So we can now actually adjust and change our focus, our alignment conditions based on, in this case, our low angle dark field, which is this one here, and our annular bright field, which is this one here, all within one data set. So we can try and tune both at the same time. I'm going to again ask Giuseppe just to make a few comments on this experience, analyzing, in this case, this GT sample, if you don't mind, Giuseppe.
Yeah, no, absolutely. Yes, it's a pleasure. Yes, yeah, we're studying this interface between these GTA materials that is applied for phase change memory. It's one of application from by the industry. This material is quite beam sensitive, and so we are interested in the atomic structure of the material, especially the interface, and we realize that the interface is very, very reactive and unstable during the observation. So with Alex, we tested different parameters, this different microscopy setup, and so probably, I don't know if you will show later on, we can see that we can play with electron dose and reduce the beam damage in order to get the maximum from the analysis in a very fast way and reliable. So this was is a very, very crucial point. It was very, very useful for this specimen.
Yeah, so
this was acquired
exactly
maybe at 20%. This was acquired at 20% of or 10%. We did two kinds of experiments, remember?
Yes, this one's the 10% acquisition.
Okay.
And what we did was we adjusted our emission current and kept the same sampling rate, and then also increased the sampling rate with the same emission current, and found that it took longer for the grain boundary to degrade as a direct result of sampling fewer points.
As you can see, yes, it's very, very stable, the interface.
Yes.
If we increase the subsampling, reduce the subsampling, we will start to see the atoms jumping from one interface to the other one. And so here instead we are observing a very, very stable interface.
So this is something during 4D STEM, being able to get real-time feedback on your alignment. There's nothing worse than when you acquire a 4D STEM data set and then you're unable to know how good it is until you've gone away, analyzed it and come back. And getting that live feedback during the scan as well, rather than waiting for a scan to finish. You'll start to see now, if you look here, here we have what we believe to be a tellurium atom jumping into either an interstitial or a substitutional defect as this grain boundary is starting to degrade. So as Nigel said earlier, when we've increased magnification, we've increased the density of sampling around the grain boundary. We start to see actually dynamics happening during 4D STEM. So we can see between frame to frame what is actually happening. So this means that, for example, in situ 4D STEM is now becoming more of a reality than ever before, without the requirement of having a super low bit depth, high frame rate camera. In this case, I would like to thank Quantum Detectors. They supplied us with the scanning generator and also supplied Giuseppe with the Merlin camera, which this was all performed on. Fantastic camera, and really helped us with this whole analysis process. I'm now going to jump on to another data set which we acquired, which is a different sample which Giuseppe can go into in more detail. So again, we're at 10% sampling.
We've got some questions that are coming in from the floor, so
okay,
just a few minutes left. So if you want to go to a conclusion, that would be great.
Yes, yeah. And then eventually we can of course do all the offline analysis using the subsample data. In this case, we're looking specifically at this region. It's confidential, so I can't go into more information. But SenseAI also offers the ability for all your 4D STEM analysis to be formed within one complete package very, very, very quickly. So thank you very much. Thank you, Giuseppe, for helping me there. And of course, any questions are welcome.
Pleasure.
Thanks, Giuseppe. Thanks, Alex. So we've got some relevant questions just flowing in at the moment. So one for you, Alex. What's the enhancement in SNR in low-dose HADAF images using your approach compared to conventional low-pass Gaussian filtering?
Yeah, so with Gaussian filtering, what will happen is those higher frequencies in your image, those higher spatial frequencies will be will be blurred down. Whereas in our approach, we're preserving that high and in fact actually increasing it by using a much higher frequency dictionary elements to reconstruct that. So in one case study, we found that we managed to improve the effective resolution by a factor of 2, just looking at that using that dictionary transfer approach from the simulated data.
And then there's one for Nigel right from the beginning is, how can this technique enhance the accuracy in quantitative EDX maps with inherently low amount of information? When quantification is done using Cliff-Lorimer method, the error will be greater than 10% for the signal to noise that we have.
Okay, but just let me give a comment on the one before as well, is that essentially when you're using any kind of filtering, you're doing it after the acquisition. So if you already have damage in your sample and you filter it afterwards, you're just going to get a filtered damaged image. The approach here is putting much lower dose into the system. So it's improving the signal to noise and it's putting less dose in there and acquiring faster images. And so that means you can move towards in situ type experiments and you're not going into the damage process. As far as the process for EDS is concerned, we can't change the physics of the process that's involved. So the Cliff-Lorimer technique has been around for a long time and it does have inaccuracies that are in that. What the method does, though, is it gives you an equivalent of a higher signal to noise. So because we can get an equivalent higher signal to noise from in-painting the missing data, then you will get as good a quantification as you can get from your system. Now, if you have something that doesn't damage and you have all the time in the world to acquire it, then you wouldn't use something like subsampling to get that to work out. However, if you want to do a big area map and you want to do it quicker, or if you're worried about damage and you want to put less dose into it, what we get from that very low dose acquisition that we're doing is the equivalent of a higher dose acquisition, which means we will get the equivalent higher quantification sensitivity for the low dose that we're using. So it still will be limited by the system, but we get effectively as if it's a higher dose system out of the work that we're doing.
Great. We've got just a few moments left. Interesting one. Just to finish off, what are the use cases in semiconductor for this technique? That's probably a half-an-hour answer to be answered in 30 seconds. But Giuseppe, have you got any sound bites or points?
Oh, yeah, for sure. Everything depends on the kind of specimens that we are using. So, for sure, yeah, industry usually, I don't work for the industry, I work with a research center that works and give a solution for the industry. And there are cases where they use material that are very, very sensitive, like the one Alex showed. In that case, yeah, but by working at very low dose, it's really, really important. And another point that I'm very interested with the technique that you are developing is the fact that, as we know, the 4D STEM benefits comes both from coherent and incoherent imaging. So this means that the data set is a huge dimension. So when I upgraded my system to do 4D STEM, company aware me in data storage, for example, and so data storage, and this means very long acquisition time and big data set. With the techniques that you are developing, and so based on what I saw during the experiment in my lab, is the impressive thing that sometimes we can get very high quality data that can be for the STEM that can be put in as an attachment on an email. So very, very small file, quite with 10% of the subsampling, and with the same amount of information or the information that we need that can be easily handled. So no huge amount of memory needed for that. I said this is also very, very, very good for companies because, as you said, keeping data center is costs very expensive. So having the possibility to have the same information and less space is for sure reduce maintenance costs.
Thank you, Giuseppe. So we're out of time. thank you. I think we could go on longer. This is a fascinating topic, amazing case study. Thanks again to Giuseppe for the collaboration and for being here today, and Alex for helping him out, and of course to Nigel as well for helping us there. And for all of you with your questions, we have, I know some people want to get in touch, so we'd be delighted to do that. The presentation, the recordings and other information, and I'm sure Giuseppe will be able to share any non-commercially sensitive stuff as well. That would be amazing. So yeah, thank you very much for your time and your questions, and we look forward to changing and enhancing the electron microscopy industry with you sometime soon. So thank you very much.
Thank you, everyone.